It's hard to believe, but this is the last podcast episode you will hear before I kick off our inaugural TWIMLCon conference on Tuesday morning with my on-stage interviews with Andrew Ng, co-founder of Landing AI and Coursera, and Deepak Agarwal, Vice President of Artificial Intelligence at LinkedIn. This has shaped up to be an incredible event with speakers from Airbnb, Capital One, Facebook, Levi Strauss, Stripe, SurveyMonkey, Twitter, Uber, and many more companies, all detailing how they're moving ML and AI out of the lab and driving real value by accelerating, automating, and scaling their ability to get models into production. It is not too late to join us. Register for TWIMLCon today using the code IWANTIN for 20% off of registration and a ticket to the hottest enterprise machine learning conference of the year. Hope to see you there. All right, everyone. I am on the line with Alex Bayen. Alex is a professor of electrical engineering and computer science at UC Berkeley. Alex, welcome to This Week in Machine Learning and AI.
Hi, good morning. Thank you very much for having me. It's fun to be here today.
So I am actually in Las Vegas, but you are no longer in Las Vegas. But the thing that kind of brings us together is you were recently speaking at the AI Summit that Amazon put together here at the reInvent conference. And so we're going to dig into your presentation. But before we do, I'd love to hear a little bit about your background and how you got involved in machine learning.
Well, I was a control theorist by training, which means essentially learning how to build algorithms to control machines, to control processes, to control robots. It's a discipline which is fairly optimization-based that finds its roots in the 90s. And so with the current revolution we are experiencing in AI and machine learning, I think it became almost obvious that all these fields are progressively merging. So you think about robotics, about perception and action, optimization, control, it's all becoming one. And so, like many others in this field, I was drawn to it because it provided a lot of opportunities for new breakthroughs and revisiting old problems with new techniques that will clearly advance the field.
Great. And so what are your research interests?
So I'm interested in two topics which are interconnected. The first one is the large-scale impacts of traffic routing apps. What happens when many people use the same apps on the road, what it does to mobility at super large scale. And then the second topic, which probably is the topic we're going to talk most today, is the notion of mixed autonomy. Is like, what do you do if you have self-driving vehicles or vehicles with some level of automation interact with manned vehicles, your car, my car, a car driven by a human. And so these two interact because if you think about mobility, obviously has a lot of large-scale aspects. How do you solve the traffic jams in LA? But mobility also has a lot of local aspects. It's like how you make traffic flow more efficiently at a local level, how you manage an intersection better, how you smooth traffic on the freeway, and so on and so forth. And both of these scales are deeply impacted by machine learning and AI these days.
Interesting. I'm originally from New York, and my wife will on occasion remind me that I am also a New York driver. To her, that has a very particular meaning. But not long ago, there was some research. Actually, it was long ago. It was many years ago. I came across some research study that said that a single aggressive driver can dramatically improve traffic flow on a highway. And I've always kind of presented her with that fact when she kind of says that I'm, doing this New York driving thing. And I've more recently seen some research that talks about, kind of applies the same idea to autonomous vehicles, like a single or small number of autonomous vehicles can also dramatically improve traffic flow. Is that the kind of thing that you look at in your research?
Totally. And we must be cousins because I'm a Paris driver. So I think we share a lot of things in common here. But totally. So it's interesting. In fact, what you're saying is so true. I would say a single driver can affect traffic very positively and very negatively. And obviously, with the self-driving features that are coming on board vehicles, we're trying to really steer the system towards a better. But we've always been in a case where, someone does something really strange and it creates some breakdown, it creates a shock wave, it creates some congestion. It creates some strange phenomenon on the freeway that we did not anticipate. That happens every day. What we're trying to do here is, in fact, the opposite, which is trying to understand how the level of automation that is progressively entering the vehicles could be used to essentially improve things. Whether it's aggressive or not, it's almost a technicality, but it's more to do something that a human might not necessarily think to do, but that is actually proven to improve things. And I think the most counterintuitive things nowadays in self-driving vehicle is that slowing down in some circumstances might actually improve traffic flow. Now, it's something that people in 2018 might have a difficult time to conceive, but it's not that different that maybe 50 years ago when someone came up, or maybe 80 years ago when someone came up with a traffic light which had a red as a color, and that meant you have to stop. Maybe people didn't realize right away, well, actually that will make traffic better because traffic lights are better than stop signs or unmanaged intersections. Well, it's exactly the same with self-driving vehicles. It's not in our culture yet. It's not even in our DNA yet. But the very same thing we've done with ramp metering or coordinated traffic light signals in cities, in New York, obviously, is one of them. That can also be applied at the level of cars on the freeways. In fact, it's something that is known and has been known by truckers for a while, because truckers are known to be flow pacifiers. They all maintain a given speed. They usually go on the same lane. That lane really doesn't have many breakdowns. It's a very smooth lane. So it's something which has been known in some, quote, sub-communities of motorists, if you will, over the years. And but that's something that with the self-driving features we see coming into cars is going to become a reality of our future driving life and have really great potential to make things much better. And that's what we're doing. We're trying to understand how AI can help solve that problem, and how can AI provide solutions which are really innovative in the way we look at that problem.
It makes me think a little bit about the concept of swarming behaviors, and in particular the idea that you can have these individual agents that have a set of behaviors that they are, whether, programmed or trained or whatever to do, but that when you put them in a system together, they can work towards some kind of broader goal. It's like the self-driving car that you're describing. It's not just trying to get its passenger from point A to point B, but it's also, that's part of the question. Is it also trying explicitly to help manage the traffic, or is that just a property or an emergent property or something that happens?
That's such a beautiful analogy, actually metaphorical and actual. First, because swarming is meant among birds, for example, to reduce drag. The reason why birds swarm is they can fly much longer. In formation, it's almost like formation flight, and reduce the drag. So it's not even a metaphor, it's real. Like trucks do platoon to reduce drag. So that's beautiful analogy of something real. But it's also metaphorical, and that's really what I like about what you just said, is that swarming, in a sense, attempts among the species that do that to optimize some cost function that might not be necessarily revealed. It's not that a fish or a bird has a cost function that they can compute, because obviously, even it's implicitly there, it's not explicitly stated in the way they actuate. But at the end of the day, the swarming achieves a higher objective amongst the swarms. And that's kind of what the self-driving vehicle approach we're following is attempting to do. In swarming, there's leaders, there's followers. So you can view this self-driving analogy in the same way. If you have, say, 5-10% of vehicles acting in a very specific way to improve the flow, you could view them as leaders in a kind of a leader-following game, in a game theoretic sense of the term. And then the manned vehicles who kind of have to react to this by kind of maybe being surprised, but okay, well, if people are driving slower in front of you, you can't pass them, so you have to drive slow as well, or followers in that two-team games. And so the swarming analogy is actually a very good analogy in that process, is that, with a small number of self-driving vehicles, we could induce the whole population to behave collectively better because of that steering that is done by these few agents that are able to work with this higher degree of intelligence in the traffic flow.
So coming back to your presentation at the conference, Can you give us an overview of the general aim and flow of the presentation?
Yeah, what we're trying to convey in the presentation is that AI is going to drive us through a few successive revolutions that are going to deeply impact the way mixed autonomy traffic is studied and eventually how it happens. The first revolution is models are potentially going away. And what that means is that if you think about the history of engineering, in every subfield, whether you work in fluid mechanics, in structural engineering, and mechanical engineering, or whatever it is, you usually start with an equation, a model of water with Navier-Stokes' equation, a model of a car, a model of thermodynamics, whatever it is. And there's been hundreds of years of people modeling these things so that you can inherit the equation and you use the equation to control it, to optimize it, to make things better. But it turns out that with deep reinforcement learning, if you can inherit a simulator that was built, by experts, you don't need to have actual knowledge of the equation to improve things. So in other words, this notion of model-free learning where you can actually improve a scoring function without having actually visibility on what the model does, but just on seeing its output is something that is going to deeply change traffic engineering. And that's mostly because if you think about the phenomena of traffic, changing lane, decelerating, routing, deciding to go or not go, stop, accelerate, all these things, they're not necessarily complicated to model, but there's a lot of different actions a human can take. So if you can get rid of all that modeling and all these Boolean variables corresponding to these decision factors and just learn over simulation, that's going to make things much easier. And that's what we showed in the talk is that, simple cases where humans have spent decades to research on how to control, with deep reinforcement learning, we could redo within a few months and we could actually beat. And that's the beginning of this first revolution where by simulation and by deep reinforcement learning over high fidelity simulators, it will become possible to solve a lot of problems that are currently unsolved with AI. And the list is long. I mean, the list could include coordination of traffic light, much better than currently done, insertion of self-driving vehicles inside traffic, control of traffic by self-driving vehicles, automated intersections, and so on and so forth. So that's the first revolution I try to explain in the talk, saying that, there's a whole legacy of work that maybe will become obsolete or maybe will just be used for other things. But there's this new body of work that is progressively emerging where we can beat the past and do things which are way more innovative. And then beyond that, there's a second revolution that is maybe a bit further away, which is, well, what if in addition to just forgetting about the models, we could learn from pictures? And that's something that a lot of people have done. I mean, obviously, supervised learning has done a lot of face recognition and object recognition and so on and so forth. Well, we're not that far from being able to do the same for traffic management and traffic control. What if after watching enough videos of traffic, whether these are videos rendered because they're part of a simulation that produces things, or whether they are actual videos, video cameras deployed in the street or dash car cams or stuff like that, over time, we should be able to learn how to manage streams of vehicles from that data and potentially from these simulations. And that is likely to be the second revolution we see in traffic control and traffic management over time. And that revolution is likely to have a much bigger set of consequences because with the ubiquity of cameras and connectivity, we're not that far from a world where every vehicle will have cameras and multiple cameras probably, and that could help the management of traffic at the scale of cities in ways that have never even been possible or conceivable before. That's what's going to happen over the next 5 to 10 years, and it's just the beginning, but that's going to accelerate drastically with the rapid pace of technology here.
So with regard to the first of the two revolutions that you outlined, I think long-term listeners of the show probably kind of know the direction that I'm going to head in and the question that I'm going to ask. And it relates to this notion of model-free. In particular, it seems to be, I guess in a lot of ways, like a very Berkeley oriented idea. And I guess I'm rarely extrapolating from maybe very few conversations. One of the conversations that I had very early on was with Peter Abeel, who, believes very strongly in this idea of kind of model-free approaches and reinforcement learning
based approaches. And since then, I kind of test that idea with a lot of people. And the kind of conclusion that I've come to is that this is a major kind of theme in where we are in the AI community, and it seems like for many, like we had this model oriented view of the world as you described that goes back many years, and then we've been more recently very excited about deep learning and deep reinforcement learning and other approaches, and have kind of thrown away the models. I guess ultimately what it comes down to is overcome some of I guess basically just get the best of both worlds, right? Overcome the computational challenges of deep learning, deep reinforcement learning, and take advantage of the many years of models. And I'm just curious, now that I've got another opportunity to talk to someone at Berkeley, having kind of put all of this together, what your take is.
Right. Well, first, go Bears, and thank you for mentioning Berkeley. Couldn't resist doing this one. It's very interesting what you're saying, because maybe the first point that is important to mention is model free works for certain things, might not work as well for some other things. And for example, you think about safety critical systems. For many years, I used to work in air traffic management. If you think about autopilot certification, about a lot of medical devices which are, safety critical, well, maybe people need to think twice about, forgetting about the model, because there's real laws of physics involved and there's real certification issues there. And so we have embraced this model-free approach for what we do, just because we have evidence that in many of the known cases, it already beats half a century or more of work of the modeling community. And we want to really point out that we use it for a very specific purpose. We are not in the business of doing autopilot, collision avoidance, anti-crash systems, safety systems for cars. These systems have a lot of different degrees of certification requirements that come with a lot of constraints. It's unclear whether what we do would apply there, and it's really not our job. Our job is to be able to come up with new methods that can coordinate hundreds of thousands of vehicles, or at maybe more local scales, maybe dozens of vehicles or hundreds of vehicles. And you could really view this as a planning tool. A planning tool, in the old sense of the term, is like you were planning train schedules or airline schedules. And if you're off by 3 minutes and you manage it properly on the ground, it's not a big deal. If your train is late by 30 minutes, as long as you have the right of way and you have the space on the railway, no problem. So here, that's the same idea. It's like probably in 99% of the cases, what we come up with will provide substantially better solutions than the state of the art. And maybe in 1%, it will do something really strange. And because it's not safety critical, well, that's not a big deal. I mean, what will happen is, well, maybe there will be 3 cars stuck on the freeway for 5 minutes in a very strange way, and we didn't understand why, but nobody died. It's a planning problem. And so I think the point is that, there's this ongoing debate that you really mentioned about model-based versus non-model-based. Obviously, both approaches have their sweet spots. I think the model-free approaches like we're using now clearly have demonstrated a very disruptive nature in the industry in which we are and in the world in which we live for coordination of multiple vehicles. But if you're doing precision chemistry or physics, we probably need a pretty good model of what you're doing, because it's material science, because it's laws of physics, and there it's maybe the story is different. The second part of what you mentioned is also very interesting, is like, well, how can we live in a place where we take the best of both worlds? And I really think about the fact that, we're not going to throw all the models and everything we've been doing for half a century in the trash right away. These can be used to accelerate machine learning in many ways. And so if you think about warm start, if you think about transfer learning, where you learn on some specific setting and apply it to a different setting, if you think about reward shaping and many different, sub approaches of making deep reinforcement learning more efficient, that's, I think, where model-based can help. there's no reason to just get a deep reinforcement learning algorithm searching in the wild when you already have a good baseline that can be inherited from the past. So in a sense, you can view this as a way to accelerate the convergence of the algorithm. And that's exactly the sweet spot in which you want, in fact, AI to augment what the human could not finish. And so maybe, half a century of research in coordination of traffic lights and coordination of vehicles and platooning and automated intersections made us come that far. And that's where it's asymptoted in a sense. And maybe the next stage is what AI brings us to. And so that's where I think the two can coexist quite nicely. And that's part of what we're doing as well, is like there's no reason to start from scratch. We could start from what the human has come up with and let machine learning do the rest.
Mm-hmm. I like that nuance in the context of reinforcement learning. The idea that, maybe, it's not worth trying to bolt these, the model together with the learner inherently, but, we can use it in these supporting functions like cold start, warm start, or giving hints of some sort, as well as the model may play a role in whatever the simulation environment is, and the way that it presents the real world to the learning agent.
Exactly.
And so the second revolution that you described, you didn't say this explicitly, but I was hearing the theme of imitation learning. Is that kind of the direction you're heading, or something else?
Well, more specifically, we're really interested in end-to-end pixel learning.
What's the distinction between those two?
Well, it's hard to make a general statement, but the one thing I could say is that in the context of traffic, what would be a holy grail to aim for is a system in which, by looking at pictures, videos, rendering, whatever it is, you can provide the same level of efficiency as by having access to the state space. I mean, so the previous part of the conversation, essentially, we maybe got rid of some of the models or all of the models, but we kept the state space. We have access to vehicle velocity, position, all the parameters. These almost disappear in an image. So if you think about a movie of traffic that either was shot from the video or from the rendering of a simulation software, that video, you could say, implicitly contains these parameters, because technically you could reinfer the speed, you could reinfer the position, but the point is they've been blended in the rendering. Mm-hmm. Or if this was a video shot from a video camera, well, you never had access to them in the first place. And so this end-to-end pixel learning to us is very important, because it would almost enable us to extend or build on the very famous work we've seen all over the social media recently about, Q-learning applications for playing video games. I mean, the Atari games, the Pong, and they were like probably the first successes. And now we see there's a lot of progress with Mario and more and more elaborate video games. And so, obviously, Pong and Atari and all these, it's the early ages of video gaming. It's still pretty simple games. But if you think about traffic, traffic is not, it's not the state-of-the-art video gaming with a lot of levels of sophistication, decision, 3D rendering, and all kinds of strategic decisions. It's something which is clearly more complex than an Atari video game. But it's not something which is on a different scale either. And so that's where we see the most interesting next revolution, is demonstrating that just by working directly on rendering of traffic, we could achieve the same performance as having access to the state space, because then that will provide proof that, well, maybe you don't need that ubiquitous connectivity anymore. All you need is an image. And then if you push this even further, onboard all the self-driving vehicles or vehicles with high level of automation, there's obviously a lot of sensing, and part of that sensing is video-based. And then there's this segmentation problem, trying to understand how to isolate pedestrians from cars, directions of movement and everything. That is a field that is moving super fast, that in a sense we don't want to touch, but we would love to at some point acquire the outputs of, once there is software out there or enough data out there so that we can recuperate all these segmented images and treat them as input for what we do. Because then we have closed the loop. Essentially, we have first demonstrated we don't need the old models. Second, demonstrated we don't even need the state space. We can just work with the image of the state space. And third, finally, linked that with the physical hardware sensing of the world, which produces these images in a way that these images can be treated in real time. And that's why I was saying a few minutes ago that it's going to take probably 5 to 10 years, because there's these two revolutions I mentioned before, but that third bridge with the rest of the community that is doing machine vision, that field is far from being solved. There's super rapid progress, but there's still a lot of work to be done for it to become operational, to run online, to run onboard the platforms, to be fast enough that it can be integrated in a real-time traffic management system. So there's all these, steps, which each of them are pretty challenging there. But I think what's really nice is to have this overarching vision of where that whole system will go within the next 5 to 10 years.
So you mentioned earlier that the models that you're building are not intended to be kind of these core control systems that are controlling the vehicle's collision avoidance, and I took it to be
collision avoidance,
fundamental
collision warning.
mobility.
Yep, exactly.
I guess I'm trying to get at. I also get the impression that you're not talking about kind of an offline, traffic system that is, looking at these vehicles and providing some analysis and telling some other system what to do. Like you're trying to integrate this into an online system. What are the relationships between these two systems, and how does that interface work?
Yeah, no, absolutely. So maybe the first part of the question, the reason why we don't do collision avoidance is it's really not our job. But also, if you think about the process of control of vehicles, there is what's called a low-level controller: acceleration, deceleration, automated braking, cooperative adaptive cruise control, and all these tools some of them have been part of our life for more than 10 years. Some of them are just coming now. A lot of it is really based on very classical control theory, PID control, lead lag. Stuff that came from the 60s that works well, and there's no reason to change it. Of course, the more recent work of collision avoidance and trajectory planning at super short-term horizons to make sure that trajectories are safe. Okay, that requires a little bit more sophistication, both in terms of the sensing and the learning. But that's really an area for which the tools you need are very specific. You need very fast controllers. You need super fast sensing loops that can provide almost immediate detection of anticipation of collisions and things like this. So the tools for that are very different. The architecture is probably also very different, because you need something to run on board on a specific chip to be certified, and so on and so forth. So that's why, in a sense, we assume that that job has been taken care of. There's the auto manufacturer, there's the autopilot manufacturer, whoever is in charge here. And our job is more the coordination. So the analogy would be, if you're running an airline, and you're doing the scheduling of an airline, you don't really care about the speed of landing of an aircraft, because that's going to be taken care by the mechanical crew, and there's essentially a controller for that. But if you're planning the whole airline, all you want is a landing window of 2 minutes. The rest, that's not your problem.
Right. I guess maybe the question that I was getting at more directly is the system that you're looking at and trying to build analogous to kind of planning, at the level of the airline, like a centralized planning system that knows about all the planes and is trying to do kind of high order scheduling? Or is it something that is, back to this distributed and swarming thing that we talked about, at the level of the vehicle, that is kind of feeding into first person navigation, but is kind of aware of these broader impacts?
Yeah. So now the question you're asking is a really deep question, and it's a question about what will the future of our transportation system look like? And that answer will be very different depending on the place and the, I would say, involvement that cities will get. So imagine a world in which maybe 5% of the vehicles are automated. It doesn't mean that the government, the city, or the company that built the vehicles can decide unilaterally to connect all of these, which is just pushing some code, and have them do some traffic flow regulation, which is pushing another piece of code and turning it on. Obviously, there needs to be partnerships. The city needs to agree that on these 10 miles of freeways, every connected car from brand ABC will automatically turn a flow pacifier algorithm that smooths traffic. And then every participant will have to, at some point, agree when maybe they buy the car or they turn on the car, like when you download an app on your iPhone or your Android, you click yes, 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 yes. In the same way, when you buy the car, you might agree that at some point you might release the autonomy of the car to a higher authority, which will do things, where things is smoothing traffic. So I think in a situation in which you have 5% of willing to participate vehicles and vehicle owners, the institutional framework in which you built an online controller, real-time controller like this that leverages all these vehicles, that's still a big institutional question mark. Is that going to be run by the state? Is that going to be run by the city, by the local MPO, or by the car company, or by a third party that is almost like a global scheduler, like the FAA or Eurocontrol for air traffic? And, if you push this to the extreme and you look at places in the Middle East, like Neom, city they're building in the north of the Kingdom of Saudi Arabia, or Dubai or Abu Dhabi, and places which are very forward-looking in the way they think about their urbanization, because they're building cities from scratch, or they're building at a rate which supersedes anything we've seen before, then you could envision networks which have a sub-portion that is fully automated, like a place where you could not go if you don't have a vehicle of a certain level of automation, say 4 or 5, and within that district, there's only 5 pre-approved models. And once you enter the district, not only does it take over your routing, but it takes over everything. Like, you punch a destination, it'll figure out the route, it'll figure out the speed, and it'll figure out how to coordinate you with the other vehicles. So that paradigm where you have automation on steroids and every vehicle is automated, that's actually much more in reach than mixed autonomy. And that's because having vehicles avoid pedestrians, bikes, scooters, cows, or whatever animal is running on the street, that's hard. That's something which is not easy to certify and to do. But having a city or a gated community or district or boulevard or whatever it is, where all the vehicles are automated and they have a specific push of the software, that's something we could do tomorrow. The technology is there. There's car manufacturing companies there that have enough level of automation to enforce that. And that's, something where an online system, like we've just been discussing for the last few minutes, is going to change mobility entirely. I mean, the notion that, you enter the center city, you push the destination, and the rest is taken care of. That's what happens essentially to a certain extent with airlines. I mean, obviously, there's ways to file flight plans. There's ways you fly, but you file a flight plan, and then the FAA will maybe give you an amended flight plan. And if there's weather, they'll have again amended flight plan. That paradigm essentially will work in a self-driving district, and that's in reach. And so you can see, walking from 5% where we're now to 100%, there'll be different paradigms. And there'll be places which are very forward-looking and will allow that. There'll be places where they will allow flow pacifiers, and there'll be places where they won't. And so the answer to the question really will depend on the city, not just the technology readiness, but also the willingness to embrace these new paradigms.
So, kind of within these 2+1 revolutions that you've talked about, what are some of the key research challenges, and which in particular are the ones that you and your group are digging into?
So every problem is hard. And that's why it's exciting to be in this field right now. And let me just list a few, which will be my top 5 of the moment. And if we talk again in a week, maybe they'll be different. So, the first thing is this notion of multi-agent learning. It's one thing to learn a global policy and to say every car of a given brand, is going to deploy the same policy. But the truth is, it doesn't work this way. There's different types of cars. There's different types of ways people want to use their cars. So the notion that we can do learning, multi-agent learning, where some are cooperative, some are not cooperative, That's inherently hard. And people who've been in game theory and non-cooperative games know this. There's all kinds of notions of suboptimality, Nash equilibria, price of anarchy, prisoner's dilemma, and many things like this. Well, these don't go away with machine learning because the uncooperative nature of the agents just make it hard. So that's one thing.
It kind of drags me right back to, this point about model free. Like, I'd love to be able to give the agent the hint that, hey, there are these, 10 things that we know from game theory that may play out here. And so if you see one of these, you can kind of get a shortcut to learning.
Exactly. And that's exactly the way we want to use game theory. For example, one example would be how you steer to more cooperativeness between the agents and how thereby, more optimality ensues from that behavior. Mm-hmm. Another really problematic part of this work is that it needs to scale up. The simulations, they're still quite expensive. I mean, if you're going to simulate the I-210 freeway in Los Angeles, it's a 5-lane freeway, 2 directions. Freeway lane carries 2,000 vehicles an hour. So essentially, if you're just standing on a bridge in the middle, you've watched 10,000 vehicles go by in 1 hour, and now that freeway extends for dozens of kilometers. So creating a simulator that is able to do this efficiently and being able to learn over that simulator efficiently is very hard. So if you're running a simulations with, say, 100,000 vehicles and you're trying to learn over it, you probably don't need to resimulate the 100,000 vehicles. You're probably going to learn over 1,000 vehicles or 100 vehicles that are actually key to what's happening there. But the process of people call this learning how to learn. So it's like there's this thing in supervised learning where, which images should you train on or what is the training data you should select to train. That's a completely open problem in traffic. It's like, is there a process by which you could determine how should you learn to learn more efficiently, given that probably 95% of what you're simulating there is useless?
So this is the whole area of meta learning, active learning, curriculum learning, all of these types of things.
And we've not even scratched the surface there. Like when I say we, is like our group. That's not, we're not there yet, just because we have so many other problems we need to solve first. But clearly, once people start to do optimization of traffic and mobility at the scale of a city, that's going to be one of the big elephants in the room if we want to achieve scalability ultimately.
Right.
And so that's another really big one. The third one is this end-to-end pixel learning right now seems in reach, but I think we've, again, just scratched the surface. I mean, we've done some moderately difficult cases, just like people with video games. They've done Pong, they've done Mario, they probably have done a few others. So, how do we make it work for real? How do we make it work for something which has, hundreds of thousands of vehicles? So that's another big challenge that make it hard. So I think what's exciting is that the rate at which innovations happen in AI is so high that there are a lot of tools that appear quite often that were not really obvious before. Like this pixel learning just had major breakthroughs, and so I think there's a hope that over the next couple of years we'll see things come from fields we didn't even think would be relevant that actually matter for what we do. And so we're far from being done, but things are moving so rapidly that I think the progress rate is quite amazing.
I feel like we could have spent, entire hours and podcasts on any of these topics.
That's true.
And so we've just kind of scratched the surface here. Any suggestions or pointers or words of wisdom for folks that are intrigued by this and want to dig in deeper?
Well, I think from a technical standpoint, we've covered a lot of ground, but I think the maybe higher level point of wisdom that I would really like to convey is that this paradigm really can only work if we have cooperation between very different animals. And these animals include, obviously, academia or tech or research, wherever that happens, whether it's in the private sector or the public sector. That's us. It involves the car manufacturing industry, because at the end, someone has to push a new release of the autopilot software to make it work in the field. And to make it work in the field means on the freeway, not in a contained test facility, like for real. And the third animal is the government, whether it's federal regulations, whether it's state regulation, MPO, city ordinance, whatever it is, there needs to be buy-in so that first it's actually agreeable to the city to operate this way. There's mobility on demand, and cars are cooperative for 10 miles where the city takes over the automation or something. So it's hard, right? Because you have academics like us that are pushing new paradigms. You have the private sector, which has its own constraint. I mean, obviously, they have to go through certification. It's got to be aligned with their market strategy. And you have the government, which essentially has to regulate and make sure that we don't kill people and that things are fair and equitable. So the word of wisdom is that we need to create a community so that these three types of animals start talking about these things. AI is changing cities, is changing a lot of different urban problems, in mostly in good ways. We've seen some cases of TNCs and mobility as demand companies, ride-hailing companies, or Airbnb styles of this world, how it can be complicated for a city to regulate over these new technologies and services. And the same is true for this mixed autonomy. And that's why it's very important to get that conversation started early so that all protagonists are ready for the time when it becomes a technological reality.
And is this conversation happening today in some centralized place, or is it just this highly local set of conversations that are happening? How can folks plug into whatever or wherever is the best place to kind of tap into this conversation now?
Yes, no, this is a super interesting question because there is no institutional place or way to have these conversations. I think what's very encouraging is that you see a lot of forums where these conversations happen. The Transportation Research Board in Washington every year, the IEEE Intelligent Transportation Systems Conference every year from the IEEE, some specific state-driven programs like the Institute of Transportation Studies forums and workshop in California, ITS America and the ITS World Congress, and so on and so forth. But the truth is, these conversations are still, I would say, boutique sessions in these venues or special sessions in these conferences. Mm-hmm. But there's not been a forum, like a worldwide forum on, how are we going to bring this to reality? And I think, it will probably emerge. I think we all have a responsibility to do this. The difficulty is that, the AI community is fascinated with research and technological advances, and that's what we should be doing. And obviously, the public agencies have to deal with the public infrastructure and policy, and that's what they've been elected for, or that's what they've been hired for. And the private sector is driven by their products. And so obviously there is common ground and there's common interest, but these are three orthogonal directions in a 3D vector space. And so it's hard to institutionalize this until there is a real need for it. And anticipation is maybe sometimes not the forte of these three actors that are working on different timescales.
It does sound like a massively complex game theory problem.
Totally is, with three players that want to be cooperative.
Well, Alex, thanks so much for taking the time to chat with us about this. It's super interesting conversation, and I look forward to kind of keeping tabs on the field as it evolves.
Thank you so much. It was a really fun conversation. Really appreciate the time this morning. Thank you.
Thank you.
All right, everyone, that's our show for today. For more information about today's show, visit TWIMLAI.com. Thanks so much for listening, and see you next week at TWIMLCon.